semantics of the platform that you have. So LiDARs can go from platforms that are meters, as in a lot of applications, to hundreds of kilometers, as in satellites. Just to give you a perspective, if we have an airborne LiDAR, these are airplanes flying around 300 meters, the resolution that you will get in XYZ is about 10 centimeters of the point cloud. The only problem with this is the limited coverage. You cannot have an airplane run around the entire Earth. You only have very localized areas. Satellites, on the other hand, are, of course, very high, 400 kilometers, and they have a global scale. They're running around in the Earth continuously, but they have a low resolution for large footprint illumination, and the measurements are very, very sparse. Just to give you an illustration of what the difference of these two measurements are, here is the point cloud that you would get at 300 meters. This is the point cloud that you get of a LiDAR at 400 kilometers. Not only do you get much sparser view, you have a lot of areas that are just not sensed, but the photons here are considerably less, right? You only have 20 photons per return, as opposed to thousands of photons in return. Right, so in earth science, there was the National Academies of Engineering and Science that put a recommendation for the next 5 years to drastically improve the need of coverage and resolution on LiDAR imaging of Earth. So the objective is to fill all of these holes and improve the resolution of coverage. So that's our project. We are developing the new generation satellite LiDARs that are going to attempt to do that. We're trying to attempt to do broad coverage and much higher resolution of LiDAR, satellite LiDAR. Right, just to give you a perspective of the problem, the state-of-the-art satellite LiDAR in this ISAT is giving you, as the satellite swats through, is giving you sensing of these blue lines. Footprints of, in JEDI, 25 meters, that's one previous generation. ISAT 2 gives you 13 meter footprints, but again, in ISAT and JEDI, you have a lot of space that you're not covering, and the objective is to really do the full coverage of the Earth. So our project is trying to obtain the green coverage, right? If we, when we started the project, NASA was interested in only getting very dense sensing of this patch. It would cover a lot more area. It would be dense and we would have pretty good reconstruction. But when our team came in, we proposed a much larger coverage by using compressive sensing methodology to expand the coverage from 1 kilometer view to about 7 kilometers view, right? In perspective, what we're looking at is how to do compressive sensing. In other words, how can we compressively sense the Earth from 400 kilometers to reconstruct a point cloud that would be captured at 300 meters, right? So that's the problem. Can we reconstruct a point cloud that you would do at very low altitude with very high resolution, but from 400 kilometers up in space? This is sort of like a graphical illustration of the problem. This is what ISAT state-of-the-art technology is giving us. This is what the point cloud at 300 meters airborne point cloud that one would desire, but you want to do this from 400 kilometers, and this is what we're suggesting, right? We're trying to do compressive sensing from this very high distance to go then from these measurements to this information. Right, so we're going to use all the tools and techniques that we use traditionally in spectral imaging, computational imaging, but applied to this problem, right? So there's a lot of interesting opportunities, a lot of interesting work that can be done in this space. In order to do this, we have to understand a little bit the differences between point clouds and waveforms, right? Because if you will, if this is a SWAT of the satellite, and what you represent here is the point cloud of the airborne, say, platform, very high resolution, the satellite doesn't measure that resolution. That satellite measures a footprint. So you can think of the satellite looking at a cylinder here that is capturing the photons within that cylinder. The diameter of that cylinder really depends on the technology. The instrumentation that we're looking at is about 10-meter diameter. State of the art gives you about 13 meters. So what happens is if you look at the photons in this cylinder and you represent them here, this gives you the information of height, right? You have so many photons that are coming back. If you're in an airborne at 300 meters, this is what you would get. But the footprint doesn't give you the spatial resolution, only gives you the photons within that cylinder. And what they do in remote sensing, in LiDAR, is they create a histogram. So from here, you get a histogram, this red line, which is the height distribution of the photons coming in. You can also get the percentiles, which is the cumulative distribution of that waveform return, that is going to give you a lot of information. Right? But this is from 300 meters. Right? So what they do, and this is standard processing in the remote sensing community, is they get these multiple waveforms, not only just this footprint, but they put, as the satellite swats through, they get this footprint and that footprint and so on, and they get a line where each of these footprints creates a 25 diameter footprint or waveform. And what we do with this, you get the histogram of that, and that creates, at a given location, creates this profile, right? So one footprint gives you this line here, which is a histogram. Then the next footprint comes in, you get another height profile, and so on. Right, so you can think of these lines up here of, in this case, are 25 meter tubes that you're sensing. And as the satellite goes through, you're gonna get a canopy profile, which looks like that. And with that information, Earth scientists get a lot of information and usefulness in trying to characterize forests and age and health and so on of vegetation. Something that's very interesting that they do is, from these histograms, they get cumulative distributions and percentiles. So from the 0th or 2nd percentile, they can get the topography of Earth, right? So if you look at this histogram and you go at the bottom, which is the 0th percentile, that's the Earth. That's how you would walk through the field. If you get the 98th percentile, you would get the canopy, the top of the forest, right? And you get other percentiles that gives you information that scientists use. So this is what scientists use today, right? But they do it at very low resolution. They do it at 30 meters per footprint or waveform, and they do it with very few photons at 20 photons per waveform, since you're doing this very high. What I'm showing here is something from the airborne, which is very low altitude. So something that we do in order to do compressive sensing, and a lot of you are familiar with, is to do 3D representations of the data. So the first thing we're going to do, we're going to go from profiles that people use in remote sensing LiDAR to hyper-height data cubes. This is a concept that in the remote sensing community they haven't studied, because they don't have the data. They don't have the mechanism to capture hyper-height data cubes. Right, so in essence, if this is the very high resolution point cloud from 300 meters, you have all the information here, and typical current satellites just get one slice of this data, right? This red line will be how the satellite will go, and that's the only thing that measures, so you will get a profile there. But we're developing a much wider coverage, so we're really going to cover a three-dimensional aspect of this point cloud. And the waveforms that cover each of these tubes we're gonna call it hyper-height data cube. We borrow this from the spectral imaging community. A lot of you know the hyperspectral data cubes, so we thought it was a cute name to call it a hyper-height data cube, which sort of resembles the same structure, right? So since we have this hyper-height data cube, we can use tensor representations, we can use all the mathematical machinery to study this information in remote sensing. just to illustrate what they do currently, they only get one slice of that height data cube. All of these satellite sensors only gives you just one-dimensional slice, right? So they look like this. And from this, as I mentioned before, they get information, right? They look at these trees that are mature in this area because you have a lot more density in the histogram on the very top. In here, you have intermediate age forests because you have more broad leaves in the middle. You can have information on the quantiles that give you if this is broadleaf trees or if these are pine trees or types of vegetation and so on. So there's a lot of information that scientists can get out of these slices, right? But they only do it in one dimension, right? What we're interested in is doing this three-dimensional hyperhigh data cube, and this is what we will get, right? This is a really new information that we're going to be providing to the scientists. Once we reconstruct the hyperhigh data cube, we can get the second percentile, for instance, and we will be providing this as the ground, right? So this reveals how the topography or the height of the ground looks like, but just the second percentile. This would be the 50 percentile, and this would be the canopy height of the forest. Right? So this is giving the scientists a complete new view, a complete new representation of the information. Right? They will be using this for topography, migration studies, carbon cycles, and so on. Now, when we go from 300 meters to 400 kilometers, the information changes significantly, right? So we would have, from 300 meters, we're gonna have a profile. If you slice that hyperhigh data cube, you're gonna have a profile that looks like this, where this is the surface of Earth. These are the tree structure that you look at. But when you go to 400 kilometers, the photon count becomes much less, right? You go from thousands of photons to only 20 or 10 photons per footprint. And what you see is, I don't know if you can see it, but this is what you would measure at 300 meters. This is what you would measure at 400 kilometers. The points are there, you just cannot see them. It's so few photons that you can barely see the information that the satellite is capturing, right? When this happens, it's because the photons, when they bounce from Earth, they go through the Beer-Lambert transmission decay that is well known in transmission of photons, which is the propagation. As photons propagate, you have an attenuation characterized by this expression. So when you have a footprint that was generated at 300 meters from these dots that are blue, what you receive at the satellite, they're going to look like these red dots. Most of those photons are attenuated and lost. What that means in the histogram is you're going to have a very noisy histogram. Instead of having this black histogram, you're going to have that very noisy, coarse histogram depicted on the red curves. Okay, so how do we do compressive sensing? How do we solve this problem with this very low resolution, very poor starved, photon starved measurements in using compressive sensing, right? What we're looking for is improvement in coverage and resolution, right? If we have a map of Earth, if we would like to have very dense footprints that I will show you the hardware how to do that, but we would like to do compressive sensing to really expand the coverage of whatever you're measuring. Right, and the technology that is used is very fast tunable lasers and optical beam steering with dispersed grading. It's really very interesting technology. It's simple, but it's really, really useful. It can allow us to either measure something that's very narrow with more photons, or you can distribute the footprints any way you want by changing the tunable laser to span 7 kilometers wide, right? And the concept is very simple. You have a tunable laser. Depending on the wavelength, it hits the grating, and that grating will disperse it in one direction or the other, depending on the tunable laser wavelength that you selected. And that wavelength can change very, very fast, arbitrary directions, right? So that allows you to really do compressive sensing, right? You would have something like the hyper-height data cube that you're interested in, that this is high resolution, high photon count, to something that you're sensing, and the sensing strategy can be anything. You can put blue noise samples, you can put more Bayer arrays, you can do optimized sampling end-to-end, you can do many things. But the bottom line is you're going to be sensing something that is much more degraded than the originally that you're interested in, much partially sampled, much fewer photons, and the idea is to go back in some fashion, right? And of course, compressive sensing requires some a priori knowledge or some characteristics of the data. And as in hyperspectral data cubes, hyper-height data cubes have similar characteristics. They're very compressible. You can have, if you have a wavelet representation, you only need a very few coefficients to represent this information. And of course, that opens the opportunity to do a lot of interesting mathematics and sampling and sensing and reconstruction. Right? The problem is very challenging because you go from something that's very high resolution, centimeter resolution in XYZ, thousands of photons per measurement, to something that has a few photons per measurement and much lower resolution in X, Y, and Z. The compression ratio is 800 to 1, right? In hyperspectral imaging, we're sort of used to dealing with, I don't know, 10 to 1. In this case, it's 800 to 1. And the reason why it's so much compression is because of the photon count, right? That's a big challenge. And also, the areas of reconstructions are much bigger, right? You're not talking about little cubes, you're talking about swaths of satellites going through Earth and trying to measure that information. So we can formulate the sensing matrix. I don't want to go through the mathematics, but in essence, you're going to have some sensing matrix that is going to do this. You select this with a tunable laser. It's going to select the patterns that you measure on top of this hyper-high data cube. And the sensing matrix looks something like this. Yeah? That depends on the tunable laser that you modulate the lasers. And of course, when you do the reconstruction, you can use model-based, or you can use deep learning methods to do the reconstruction. But because it's so much compression, we first attempted to do deep learning approaches to do the reconstruction. So we're going to do a learning model to go from measurements at 400 kilometers to reconstruct something that you would see at 300 meters. Right? That's the goal. What enables us to do this is data. Right? For the learning model, you need data, and NASA has this data. Right? NASA has the data at 300 meters, and they have large quantity of areas of the United States. You have thousands of kilometers of airborne data, and they have the satellite data as well. Right? So you have all the components for machine learning, and we're going to tackle that problem from a learning mechanism. Right? So we're going to use a learning approach using some cost function, and that depends on what architecture you select. We're going to have over 1,000 kilometers of point clouds for training and testing in many regions of the US and Mexico. As I mentioned, this is a lot of quantity of data, so we're going to initially separate the reconstruction by patches, and we're going to do that, but that's a problem that NASA is looking at, how to optimize the data, the massive data that has to be accounted for. In selecting the deep learning mechanisms, we of course use starting from the autoencoders because it makes a lot of sense. You have missing waveforms. The latent space will get rid of the missing information, and you can reconstruct this fairly well. So a lot of the results I will show you is with autoencoders, but we are generating a lot more results with other architectures, and I will show you some snippets of that, and the results are amazing in some of those other architectures. So most of you will know what the autoencoder are. You know, you have the the data, you put it through latent space, and then you build it up. It has these three-dimensional convolutions and so on. And for experimentation, we selected 2 regions of the US. We selected Oregon and Florida. For those of you that are not too familiar with the geography of the US, Oregon is an area with lots of mountains, lots of diversity of heights and lows and rivers and so on. Florida is much flatter. It, of course, has vegetation. All of these have vegetation. So we're going to do these results in these 2 areas, although we have done many, many other regions of the US and Mexico. So from this, we get the data that has, NASA has the data, and we train 2 neural networks. We have to train different neural networks for areas of the United States, right? So the Mid-Atlantic area is one network, the Northeast is another network, Florida in the South is another network, and so on. And the landscape look like this. You know, they're very, very different. So these are the results, and this is what you would sense at 25% spatial resolution sampling, right? I normalize the colors because this is so many less photons than the ground truth, just to show you what the points are. I mean, but if I put the real the real scale, would barely see this data. This is what you're looking for. It's the digital terrain model. This is how the bottom of the Oregon looks like. It has about 240 ups and down meters on the landscape. And what you're able to reconstruct with 800 to 1 compression is this information, right? Which is remarkably accurate. This is the error plot between these 2. And this is the canopy height. This is what the top of the forest in Oregon sensing. This is what the canopy height model looks like. This is what we are able to reconstruct, and this is the error. Right? If you go and look at one of those slices, you know, this is what photons you're getting, this is the ground truth, and this is what you're recovering. So it's a remarkable reconstruction. Right, so when NASA saw these results, they were, because they were not too familiar with this computational imaging in this lighter remote sensing community, and they were, really excited about looking at these results. If you go to Florida, this is a little bit different because in Florida, the ground is pretty flat, and the vegetation, of course, changes. But this would be the sample of the sampling of the satellite. This is the ground truth of Florida. This is what you're able to reconstruct, and then this is the error. Very smooth. The vegetation, when you do canopy height model, is, again, this is the sampling at 25%. This is the autoencoder. I mean, this is the ground truth, and this is the outer encoder restoration. Something you would see, it's a little bit blurry, right? So autoencoders typically introduce some blurriness on your reconstruction. And you will see it here, right? This is the across the swath information. This is the measurement. This is what the ground truth is, and this is what you're recovering. And you can see a little bit of blurring here, right? The same thing here. This is what you're measuring, the ground truth of the Florida slices, and this is what you're reconstructing. You can see a little bit of blurriness on the autoencoder reconstruction. So if you look at the metrics, it's very interesting, right? You have in the Florida, and you do an MAE of digital terrain model, you have a 0.06 meters of distortion. So this is fairly accurate, right? This is the meters of distortion on the ground truth. If you do the same thing on Oregon, of course, since the Oregon has much more variation on hills and so on, you get a 2 meter distortion on MAE, but that's justifiable because mountains go to 260 meters up and down, so you have, of course, you're going to expect more distortion on Oregon than in Florida. We also looked at, the little smoothing effects of the autoencoder, and we're looking at some of the more advanced machine or deep learning algorithms. The transformer is one that is very interesting architecture. This is the ground truth, this is the autoencoder, and this is the transformer, using the same amount of data. But of course, the transformer requires a lot more data than the autoencoder, and that's why we're not getting significantly more resolution here. We're going to expand the amount of data to do the training, and we expect to have a lot more results and resolution in this reconstruction. Then we go to generative process, right? We looked at GANs, and this is where really the performance improved significantly. This was a quantum leap on resolution gain, right? This is what the input, you're measuring the reconstruction of canopy height, and this is the ground truth, right? And so this is what you're measuring. You barely see the photons there. This is the reconstruction. This is what your reconstruction with GANs, and this is what the ground truth gives you. And look at the resolution that you gain there, and it's just mind-boggling, because here you're getting 0.25 meter resolution height, which is unprecedented for satellite LiDAR. My colleagues at NASA are saying, we don't know what we're going to do with this resolution. They are used to getting data with 0.7 meter resolution. Now we're giving them 0.25 meter resolution. We're also giving them 3 meter resolution spatial XY. So they were used to getting the information at 13 meter resolution. Now we're getting them at 3 meter resolution out of this generative process. So I think this is really mind-boggling, and we're continuing to improve. I think we can, we're looking at some other mechanisms to even further improve that resolution. We're hoping to get to 2x2 resolution. So in conclusion, you can see that the drastic improvement from current state-of-the-art LiDAR, satellite LiDAR measurements on Earth. We're proposed and we formulated the compressive sensing approach, going from this compressive sensing to the high resolution aspect that the National Academy of Engineering and Sciences is recommending. They're recommending drastic improvement in coverage and resolution, and that's why NASA is developing this technology. A lot of this work is just possible because we have data, right? Data is critical, and NASA has a bunch of airborne mission high resolution data that's going to feed the machine learning or deep learning reconstructions. What is mind-boggling, for me at least, is the compression, right? 800 to 1, when most of the time in spectral imaging or X-ray imaging and compressive measurements, I was used to having, 10 to 1 or that order of compression, not 800 to 1. We have looked at many architectures. GANs are just something that I'm really excited about. I think those are very interesting architectures. We're also looking at end-to-end optimization. All the results I've shown you are sampling mechanisms that we know will work well, but they're pretty static. You put blue noise masks and you do the sampling. Very easy, trivial, but you can do a little more fancy sampling to do end-to-end optimization. And we're working with our team that they already built these satellite systems. They have them on Earth. They're doing the measurements, but they're doing them on Earth. Right? So they go to these big, tall buildings, and they shoot the lidars, and they try to measure objects at very large distances just to calibrate and make sure that everything works before they send up to a satellite deployment. Right, so in general, this is a Well, interesting project that we started about a year ago. I think it opens some new opportunities in computational imaging. There's lots of problems, lots of opportunities to apply mathematics, reconstructions, and all the tools that we have been using and developing for the last 10 years or so. So with that, I thank you for your attention, and any questions I'll be glad to answer. Yes.
Hello. Thank you, Professor Arce, for the presentation. Very nice talk. I noticed the effort in this talk. I suppose that it's both wrong and very difficult to solve. But I think if NASA maybe have some satellites with different modalities, I suppose spectral imaging, RGB imaging, and something like that, that have a different resolution, that maybe you can take a lot of information in order to improve your resolution. Are you trying to mix some modalities of the Earth?
Yes, that's a very good question. Yes, indeed, the platform that is being deployed will have spectral imaging at high resolution. And yes, we're doing the multimodality optimization to the results I show you are 3-meter resolution reconstruction only using LiDAR information. We're going to improve the reconstruction with the spectral information that we get. So yes, we can do that for also end-to-end optimization, because the spectral information gives us vegetation indices, right? There's a lot of vegetation indices that tell you where are you looking in vegetation. So you're going to sample, or you're going to send your footprints more in that area than perhaps in areas that are flat, there's no vegetation and so on. So depending on your application, you will be able to do sampling optimization, and we're doing that. That's a very good question. Mm-hmm.
One question. I understood that the imaging from the satellite is obtained only 552 nanometers, right?
It depends. In the state-of-the-art satellite currently, ISAT-2, they use 500 nanometer because that penetrates water better. The one that are being built now is at 1,000 nanometer for some other reasons that they selected that wavelength.
Okay, and then you are trying to reconstruct the intensity of that information across the whole area, right?
Yes.
Maybe you found better results in the visible region or in the infrared region.
Yes, absolutely. And that's how they select the wavelength is very important. In ISAT-2, they were concentrating in Arctic and ice and water. That's why they selected the 500 nanometer. When you go to vegetation, they found that the 1032 or something like that is a better wavelength to sense leaves and vegetation and so on. Yes. Water is the green wavelengths. Yes. That's a good question. Dave?
I want to ask about the reflection model. Like, do you assume like it's a Van Bergen reflection, and in the data, do you see some kind of artifacts that might be associated with speculative reflection?
We are assuming a more simplistic approach in our sensing. When we do the modeling, we just assume that there's a attenuation, and the attenuation is uniform, and but we haven't really done a very extensive physical modeling. In the machine learning, we sort of ignore that because it's data driven, right? You get you send the measurements. This is what we collect, and the machine learning tries to learn the mechanism as it works. But if we are going to do a model-based reconstruction or iterative, more iterative algorithms that take into account the sensing matrix, we need to go into more depth, as you say. Yeah, but that's an area that we're looking forward to do that. Yes.
Professor. Thank you for the talk. I was wondering if on the ongoing work, if the end-to-end optimization, are you just optimizing the sensing matrix, or are you optimizing the full architecture of the satellite?
Yes, the optimization on the A matrix is important. In what we have done to this point are two things. We have used standard sensing patterns. We know that blue noise patterns work fairly well. They're not optimal, but they work fairly well. NASA is interested in looking at a broad spectrum of solutions, something that is very simple, very easy to implement in hardware, to more advanced optimization methods of sampling. We're also doing end-to-end optimization, where we're taking into account the spectral information, the indices of various vegetation modes, or what they do in carbon measurements and so on, in order to optimize where you send those pulses. Right? So that's an active area of work, and that's what we're doing now. Yeah, good question.
Thanks, Gonzalo, for a nice talk. I have several questions.
Mm-hmm.
So the first one is that it seems that this slider from the satellite seems like a lucky magic thing. So you only get a few photons back.
Mm-hmm.
So these are the ones that make through the atmosphere.
Mm-hmm.
So and atmospheric turbulence have different, statistics depending where you are, and depending on weather or the season. So my question is, if you're training for a particular, let's call it this way, this compression, because this is what the atmosphere is doing for you. So I'm wondering if you take data from a completely different place, a dry place, a desert, if it will hold, because you're training for a completely different mind.
Yeah, absolutely, absolutely. You're right. Our training has to be done according to the data structure, right? So if you're looking at the Florida regions or the southwest of the US, or you're looking at Oregon, you have to train different networks. And that's what we've done, right? We look at, according to their recommendation, NASA tells us, these are the areas where they have vegetation that is similar in terms of trees, in terms of vegetation. They want to train one type of network. If you're going to go to Florida, which is completely different, then you have to do your retraining again, right? So that's the solution that we have to date. But there may be other ways to maybe generalize that a little more.
Okay, also, in some of your results in the reconstruction, I don't know if it's slide 32 or something. Oh, this one.
No?
Later? No. Oh, that one. You have another one next? Oh, okay, yeah. So the reconstruction is in the middle, yeah?
Yes.
So on the ground truth on down. So
Yes.
You can notice some sort of artifacts, like some green kind of artifacts on the blue part, you see some dots like green.
Okay, right.
So how do you perform your construction? You do it like in a batch base? And
Yes.
then you merge them, or
Yes.
how do you do that process?
Yes, at this point, because the data is massive, and that's something that we need to address. We haven't addressed that problem yet. We are segmenting by patches, by 32 by 32 by height patches, reconstructing and then patching it together. You get a little bit of artifact, but we are doing some overlaps. But that's an area that we need to improve a little more. Yes.
So my final question is, what happens in areas where we don't have photons back at all? So you have no information.
If you have what? No photons.
When you have no photons back, I imagine a very dense area. So you will never touch the ground. So you never have a photon that goes to the ground and goes back. So you cannot do any of the, of your histogram stuff. So what happens then? You're inventing information?
Yes. Yeah, this is where the generative network is amazing. If you look at this is the input, right? So we are skipping ground. If you go from here to here, we're doing super resolution. The measurements included areas where you don't see anything. You don't see any waveforms at all. And when you reconstruct, and this is the ground truth from the airborne data that tells you this is what you're supposed to be reconstructing, even though you haven't seen the data, and this is what the GAN gives you, right? So really, the GAN is predicting, inventing things, what it should look like. Yeah, and not only in XY, but in Z, because when you do the measurements, you're really doing measurements at only capable of doing 0.7 meters. When you reconstruct this data, is doing at 0.2 meters. So it's an amazing super resolution result that the GAN is giving you. Yeah? Significantly better than autoencoders and transformers and so on.
Oh, thank you.
Mm-hmm. There's a question there.
Thanks, Professor, for the talk.
Mm-hmm.
I'm interested in going about the sampling statistics. I noticed that you use blue noise and the other one. Can you talk a little bit about how much those statistics influence your results?
Mm-hmm.
I noticed also at the end that you are going to plan to use end-to-end approach. And in that approach, you design both the acquisition and the reconstruction.
Yes. The idea was to begin with sampling patterns that work reasonably well. In our experience in spectral imaging, we know the blue noise sampling patterns are fairly good. They're not optimal, but they're fairly good. And they're simple. Right? There's simple matrices. You just do threshold and you get the results. You also get other patterns that are generalized Bayer patterns that also have a good distribution pattern. So those are the two patterns that we initially looked at. And the difference is that you get, this is Bayer type patterns, these are blue noise patterns. In most of the cases, the blue noise pattern gives you better performance, right? You get a little better noise in the MAE and so on. So in general, we found that blue noise patterns work better. But that's just the first step. As a second step, we want to use site information. As Jorge was saying, we have availability of spectral information, even panchromatic information, that can not only tell us where to send the footprints, but also to improve the resolution of reconstruction, right? So at this point, we're getting 3-meter resolution spatial reconstruction. With site information, we believe we can increase that resolution to maybe 2 meters resolution reconstruction, right? And that's something that is mind-boggling to the remote sensing community in LiDAR, because all their studies are always based on 13-meter resolution, 70 centimeter resolution and height. Now, when we show these results to them, they're telling us, I don't know what we're going to do with this resolution. They never thought about it, right? So it's really interesting for them. But yes, there's going to be sampling patterns that are going to improve resolution and image reconstruction. Mm-hmm.
Thank you, Professor. I have a question about the physical limitations that make the pattern sensing the LiDARs satellite. Can you show the slide with the comparison between the satellite and the airborne? Yes, the ISAT satellite have that pattern, that lines in the pattern. But what is the physical limitation that impose that, and if it is possible to implement hardware these compressive LiDAR sampling?
Yes, this is state of the art, and if you see, you will see 3 lines. You see these lines here? There's three lines going through as the SWAT satellite goes through, and those are the separation of when the pulse is sent. They go through a diffractive element, and that pulse is separated into 3 pairs, and that's why you're looking at these 3 pairs there. That's what one swath of the satellite would look like. These other lines are much later, after weeks where the satellite is going around Earth, you're going to collect more spatial data. So in weeks or months, you're going to get these lines, right? This thing here is the compressive sensing measurements, but they're going to be much broader because with the tunable laser, you will be able to direct those pulses 7 kilometers away, right? So you can make this much broader, very sparsely, but with the machine learning, you can reconstruct everything in between, right? So this will be the measurements, and this is what you would be able to reconstruct. I'm not sure if I answered your question. I mean, the reason how you can do that is because of the tunable laser in the diffractive element that's sending the pulses where you want them in that very broad coverage.
As I understand, you sacrifice like resolution locally, but increase your field of view?
The resolution that you get is and spatial resolution is determined by the radius of the pulse that you send, right? So ISAT has, I think, 13-meter diameter. The hardware that is being built has 10-meter resolution, but because the modulation overlaps those pulses, when there's some overlap of those pulses when they send, then computational we reconstruct a 3-meter resolution. Mm-hmm.
Thank you.
Mm-hmm.
Thank you, Professor, for the talk. I have a question about what type of noise distribution is developed in this type of acquisition system.
Can you repeat the question? I couldn't hear you.
About the noise, the more important noise that is present in this type of acquisition system.
Yes, of course there's noise, a lot of noise in these measurements. Some of it is canceled in the detection. There's once the photons are received, they're put through these optical fibers, and those are they're passed through a very narrow wavelength filter. So anything that's slightly above or below the 500 or the 1000 nanometer 32 wavelength is deleted because you have noise from the sun, the atmosphere, whatever, other types of noise that's filtered out. You still have some noise due to the time of flight information, and that's also considered when you do the processing. For instance, to do the digital terrain model, you don't get the 0 percentile because you will sometimes find photons that are giving you information that Earth should be below what it really is. So the digital terrain model gives you a 1 percentile to filter out those fluctuations on noise.
Thank you.
Mm-hmm.
Hello, doctor. My question is about the sensing matrix. Because you know some matrices like the strict Fourier transform, the Gaussian one satisfies the restricted symmetry property. So for your sensing matrix, you have a guarantee of reconstruction or under certain conditions?
Yes. The reconstruction approach that we're doing now is learning based. So we are not considering the theoretical properties of the RIP and so on for the sensing matrix. When we start looking at the model base, that's when that will play a role. Our intuition is, you're doing randomization on the sensing hyperheight data cube. You know that the hyperheight data cube has sparse representation on wavelets, and we know that, for instance, the blue noise characteristics satisfies the restricted isometry property in the hyperspectral imaging problem, which is almost very similar to what we're having here. So we're pretty confident that we will also have those theoretical guarantees. Okay, so I want to thank you again for your attendance. It's a pleasure, and I look forward to talking to you during the conference.